Welcome to Soft Earth 3, everybody. The cute title is Things Fall Apart. The maybe more instructive title is The Geometry of Failure. So with the exception of this lecture, all of the lectures that we do are about soft materials, soft modes of deformation. That's a term that I never define once for you rigorously. I sort of define it immersively through the series of lectures. Today we are going to talk about a mode of failure which is not soft, right? We're going to talk about a classic mode of failure for like hard materials, which is fracture, right? Which we usually associate with brittle stuff. We have to talk about it, number one, because I like it and I've worked on it. But number two, we have to talk about it because we live and walk on a planet that is predominantly granular, right? There's soil and sand and rocks and stuff like that. Most of the surface of the planet that we walk on, if we could go to the bottom of the ocean, you find oozy mud and stuff. This is granular particulate stuff. Planet Earth didn't start that way, okay? So planet Earth did start out with solid rock, and the process of fragmentation is the process by which solid rock gets broken and shattered and ground down and turned into the particles that cover the surface of the Earth today. And so it also makes sense for us to give some heed to that. All right, so again, we're going to start with the planet Earth, and we have this idea about plate tectonics. I'm going to draw my terrible cross-section of the Earth again. So you imagine that we have the core here, which I'll keep saying we don't care about. Then we have the mantle convecting, which we do care about because it drives plate motion, right? And then on this side, we'll say this is like the crust, right? So you're sort of looking at a cutaway of the core. And this crust. So in the beginning, right? Earth actually condensed out of granular material, a bunch of asteroids and rocks smashing together and melting, right? When those rocks smashed together and melted, it differentiated, so the really heavy iron went to the bottom, right? That's the core. The slightly less heavy elements went into the middle and combined to make the mantle, and then the crust is the lightest stuff, which is on the surface and is brittle, right? And imagine that in the first X number of millions of years, planet Earth was a magma ocean. So the liquid rock was not just in volcanoes or not just in the mantle, it was all the way up to the surface, right? So we had a planet covered in a magma ocean. We don't really know what was going on, how it was moving, how it was swirling, but it was a magma ocean. But of course, that planet was losing heat to space. And so eventually, this lightest material, which was the crust on the surface, was also the coldest, and it congealed, and it made a solid shell, right? And Earth, for a moment, was like a perfect eggshell in the crust, right? Smooth, solid, wonderful, paradise, right? And then the shell cracked. Now, there are debates about the cracking of that shell, right? One going model is just that because of the chemistry of this crust and the loss of heat, it's solidified, but the moment that a crust differentiated and solidified, now we had this rigid, hard lid. We still had heat that was diffusing and convecting away from the core through the mantle, and that we started to get a buildup of heat against this shell. And so the idea actually is the shell froze, solidified, and then thermally expanded because of the heat that was trapped underneath. And it was this perfectly isotropic expansion that made it crack, okay? We weren't there to know. All these best guesses come from simulations, but when that shell shattered, it was like a paradise lost, right? We went into a situation where we had this cracked shell, and now we enter the beginning of plate tectonics, what we know today, right? Once this shell cracked into these individual plates, they're now being driven here and there by the mantle convecting underneath and crashing into each other, right? And doing all the things that we know and love, right? So I want to make a point that this fragmentation, which was cracking of the Earth's shell, it created a planet that is a fracture mosaic, right? The shell cracked into mosaic of cells that are each bounded by the fractures that made them. And that process first happened at global scale, and that process has been playing out across all scales and at ever smaller scales, right? And so this is sort of the original fragmentation of planet Earth, and the fact that it set up plate tectonics and set up collision and mountain building and rocks getting exposed and breaking means that it kind of kicked off subsequent fragmentation as well, right? But of course, we see cracking in a lot more mundane materials, right? So we see cracking in mud, right? If you take a bunch of mud, take some, which is just some swelling clay and water, which we'll talk about, right? And you let it dry, it will make these hierarchical networks of cracks, right? So we see this in mud, which is really just a mixture of clay plus sand plus water. We'll talk about the mechanics of that in a little bit. But that's not the only place that we see it, right? So another thing is that when we go to places like the Arctic, you can look at the surface and you'll see what we call polygonal ground. And so it kind of looks like the tectonic plates, but in miniature. And so you look down, and this is all soil in here, and you see that the soil is organized into these polygons. When you understand and you look closer at what that's made of, you see that it's soil plus ice. And so the idea here is that there's some thermal changes that are happening. The ice expands and contracts. The ice is mixed in with soil. And that soily, icy mixture breaks, and it makes these classic polygonal patterns, right? We see it in ice, right? So you can look at a frozen pond, or you can look at an ice sheet in Greenland or something else, and you see that the ice is crisscrossed, right, with these cracks. We'll talk about that ice is interesting and a little bit distinct from some of these other materials. We'll get into that. And then, of course, you see it if you just walk up to a rock outcrop, right? So if we walk up to an outcrop of rock that has all these cracks and joints in it, you can look in front of it, and what you'll see is this talus pile or this scree slope that has all of these polygonal-looking blocks that are piled up in front of it. Right? It's the fragmentation of this rock. When these cracks connect together, the rock becomes liberated, right? The pebble falls out. And if you zoom in on this process, we're not really going to talk much about mechanics, but we'll just talk a little bit. That the thing that's going on is that, you know, what I want you to understand is that when you have a crack in a material, however it starts, that stresses get concentrated at that crack tip, right? So if you were able to measure the stress field, which is very hard to do, but we can do it in simulations, you get this kind of halo around the tip of the crack where the color corresponds to intensity, right? So the idea is that if I push on this rock and I make it deform, that the rock is going to deform and strain a little bit, and through that process, it's going to concentrate the stresses at the tip, right? So wherever I push on this rock, you can imagine that strain or vibrations or whatever are going to travel on this interface till they get to that point. And so stresses actually get concentrated at that tip. And because the stresses are concentrated at that tip, the tip will grow. And when that tip grows to the point where it percolates through a sample, then the sample falls apart, right? So the macroscopic process of fragmentation is related to this microscopic process of concentrating stresses at the tips of fractures, okay? Now, if we look around, we see the products of fragmentation everywhere, right? So, you know, one classic example we can think of is just pebble transport, right? So if I have, imagine that this is a hard bedrock surface of a river. The flow is going in this direction, and I have some particle that comes and, you know, I'll draw little bam lines, right? Bam, collides with the bed. So at the point where that particle collides with the bed, we know that there's an impulse that propagates cracks right there, right? And so one way to get fragmentation is at a very local scale of just moving pebbles downstream in a river. The pebbles smack into the bed. That repeated smacking just develops fractures at each point of collision. And each time it smacks in, those cracks get activated and they grow, okay? So rivers is one common place where we get fragmentation. It's not the only one. So at a larger scale, right, we can look at volcanoes. Volcanoes typically will have a little chimney of liquid rock that comes up, right? But the liquid rock comes up and it can solidify at the surface, so you get this plug, right? So you get a plug of solid rock and you have hot liquid rock underneath that wants to come up. So it's heating, heating, heating. It wants to convect and come up, but it's stuck. And eventually, bam, right? It breaks loose that plug, and that plug turns into a bunch of shattered pieces that go flying out, right? And so fragmentation is going to happen there, right? And you get this explosive fragmentation from volcanoes. These can make pyroclastic flows that flow out with hot gas and fragmented particles together. They can make the ash, right? And so this is producing a huge range of sizes from micron scale ash all the way up to giant boulders that can get flung out. The boulders to the flank, the ash, of course, can travel around the world. And just maybe to zoom out and get a little bit spacey. So we know that there are asteroids that are essentially what we call rubble piles. Some of you might remember, I don't remember what the year was, maybe it was 2018, 19, when we landed on the asteroid Bennu, and there was a sample return mission from the asteroid Bennu. And we thought we were dealing with a solid, competent asteroid that we were going to land on and get a sample. And it turned out that when we got there, we started orbiting around it, that it was just a rubble pile. It was a bunch of fragments, really angular boulders that were just barely held together by gravity. And it turned out that it was very hard to land on. It was very hard to get a sample from. So there are rubble pile asteroids out there that are basically just made of fragments that are litter from previous collisions. And even the planetary rings of Saturn are icy bits. And when you look at them closely, which we have now with Cassini, we see that they're fragments. They're angular polygonal fragments. They were somehow formed by fragmentation of ice and then got stuck around Saturn. And so I just want to make the point that across scales, across planets, fragmentation, you can almost think of it like entropy, right? The moment that you solidify rock or ice, it is going to experience stresses. Those stresses will eventually cause it to fragment. And so fragmentation is producing, like the byproducts of fragmentation are basically covering our planet, covering other planets, and even literally orbiting other planets and making little planetoids, if you will, right? So I want to get a little abstract for a second. I'm going to disappear from the camera just to get an eraser. Don't get nervous if you're here on camera. All right. So I want to think about fracture patterns, and in particular networks, in a rather abstract way. And then I want to show you that that abstract way of thinking is actually helpful. So first thing is that we are going to focus today on 2D fracture patterns. Anything that you learn today can be extended to 3 dimensions, but we're going to talk about 2D. It's just easier. So what do I mean by 2D? So let's take these mud cracks over here. What I mean by 2D, nothing in nature, of course, is truly strictly 2D. Only our drawings on paper are strictly 2D. But what we mean is that, right, you imagine the size of a fracture mosaic that's made of mud, for example, and we'll call this L, some characteristic length scale, and we'll call this the thickness of it h. And so 2D for us just means that h is much less than L. And the reason that that matters is it just says that when I look at the surface, I can presume that this material is thin enough that any crack that I'm observing on the surface goes all the way through, right? So we're essentially assuming that there's no variation or anything interesting happening in that third dimension. Now, that can sound like something I'm just doing for convenience, but if you look at mud cracks and polygonal ground in the Arctic or ice sheets or the tectonic plates, all of them pretty well satisfy this two-dimensional assumption, okay? So there's a lot of fracture networks that we care about that are 2D. So I'm going to tell you something first. You're going to have to believe me, and then we're going to explore the consequences of it, and hopefully through the consequences you will come to actually believe me. All right. So the thing I'm going to tell you is that these 2D, we're going to call them fracture mosaics. And I like to call them mosaics because it says, you know, you can think of it as like, this is like a tiling, right? So when you think of a mosaic, think of a tile mosaic. And all of the tiles need to fill the mosaic and leave no space, okay? So we're going to call these fracture mosaics. And what I'm going to tell you to just believe me for now, and then we're going to use this assumption I'm about to tell you and explore it and see if it works, is that fracture mosaics are tessellations, is an important word, and we'll come back to it. They are tessellations of convex polygons. So the tessellations part means that these cells in these mosaics fill all space and leave no gaps. That seems kind of obvious, right? If you think about a plate that you drop on the ground, the moment that it shatters and before it flies apart, we understand that there was a solid plate, so all the fragments that it made need to fit together and fill space with no gaps, right? So that's all that a tessellation is. It's a tiling that fills space and leaves no gap. The convex polygons part means that they are convex polygons, no concavities. So think, you know, triangles, squares, rectangles, hexagons, dodecahedra, whatever, right? So this is a convex, that's a terribly drawn one. This is a convex polygon. This is an example of a polygon that has some concavity in it, right? Of course, fracture networks, I'm not saying that there's no single crack in them that doesn't have concavity. I'm just saying that these are all extraordinarily well approximated as tessellations of convex polygons. They are so well approximated that you really don't lose anything by drawing convex polygons around all these natural mosaics and then using that description. The reason that we want to do that is it turns out that there's some beautiful geometry about convex mosaics or mosaics made of convex polygons, and using that beautiful geometry actually explains some features of natural fracture patterns. All right, so there's some very classic problems related to tessellations of two-dimensional surfaces with convex polygons, right? But for us, we'll just start with the simplest scenario, right? And remember, I'm bad at drawing hexagons, so don't get mad at me. We're going to start with the simplest scenario of considering the geometry of tilings of 2D polygons. And the simplest case, we're just going to say that they are all regular polygons. So all sides are the same length. And they're also uniform, meaning that tilings that are made of triangles that are all the same size, right? So if you are using regular polygons, the only regular polygons that can tessellate and fill space and leave no gaps are triangles, rectangles, including the special case of a square. So in this case, you can relax the regularity. It doesn't just need to be a square. You can do it with rectangles too. And hexagons. They're the only three regular polygons that you can fill all space and leave no gaps. Okay. If you just look at the mosaics that I've drawn, they're suggestive, but none of them are perfect triangles, right? Or hexagons or squares. So I don't draw these shapes because I think that they actually exist in nature, but I'm going to tell you how understanding them is the beginning to understanding the shapes in nature, all right? So we're going to ask the question then, how do these shapes tessellate, all right? So if we consider first the triangle, all right? So there are a couple tessellations of triangles that you can make. Right? Trying to draw them as well as I could. This is one, right? So you say, right, there's a, let me draw this up here too so you can see them, right? Triangle, 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 right? So we would all agree that that's a tessellation that fills space, right? And I'm going to introduce a way of counting here, all right? So the way of counting is first what we're going to do is we're going to count the number of vertices that each one of these has, okay? So it's a triangle, 1, 2, 3. Of course, all the triangles are the same, so you can count the vertices in every triangle. They're all going to be 3, right? So we will call V the vertex degree, which is the number of vertices that each tile has. And that number here for the triangles is 3, right? Now, the other thing that we can introduce is what we call the nodal degree. The nodal degree asks how many vertices meet at a node or a junction, right? So if you count this, you would have 1, 2, 3, 4, 5, 6, right? So we will call that nodal degree 6. Now, if this is a regular convex mosaic, every node has nodal degree 6, and every cell has vertex degree 3. So whether I describe the numbers for individual nodes and vertices or I describe the average for the whole mosaic, they're going to be exactly the same, right? That's not going to be true for these mosaics, the natural mosaics. They're going to have variation, right? But in these, it's simple. So that's one way to tessellate with the triangle. The second way to tessellate with the triangle is that things don't line up, right? So if I have triangles like this, that underneath them I have triangles like this, and you can check and say, if my drawing isn't terrible, that all the triangles are still the same size. And because they're triangles, they're the same shape, so the vertex degree does not change, right? It's still 3, no problem. But the nodal degree changes, right? Because now if we count, we have 1, 2, 3, and then that's it, right? So triangles give us 2 ways that we can tessellate space. The fact that they're triangular means that the vertex degree doesn't change, but they can fill space, and they can either line up perfectly and make nodal degree 6, or they can line up not perfectly any other way and make nodal degree 3, all right? Now, let's consider now the rectangles, right? So rectangles can go a couple ways. So one way that they can go is what I like to call grid paper, right? So you can verify that all of these rectangles are the same. You can count up the number of vertices, and of course, it's going to be 4. And if you count up the nodal degree here, you'll find that it's also 4, right? That's not the only way that it can go, right? So you can also make rectangles where things don't quite line up like that, right? I like to call this the brick wall pattern because of course this is how we make brick walls. And they're made of the same rectangles, so the vertex degree is still 4. But then the nodal degree, if you count it up, if my lines don't jump over, is 1, 2. Right? So far, this is all simple, right? We're just counting. Now, we only have one more shape that we can explore in these regular tessellations, and that is the hexagons that I'm terrible at drawing. And if you draw out hexagons and you fit them together, you can demonstrate pretty easily that there's only one way to tile them, right? So count up the vertices. Of course, we know what they are. They're hexagons. Oh, wait. I used a different color. Let me do this. There we go. So count up the vertices. We know it's 6. No problem. Count up the nodal degree. 1, 2, 3. All right? So we went through this exercise, and we figured out what regular polygons can do. What we realize in this counting exercise is that we see here all the junctions are X junctions. We see here that all of the junctions are T junctions. And we see here that all of the junctions are Y junctions, right? You'll see that I'm not labeling these junctions. It turns out nature doesn't like these. Nature doesn't make these, but they're helpful for us to understand things. All right, so I want to now make a simple plot that is a way of characterizing this geometry in a simple way. And so we call this plot the symbolic plane. And what we do on the symbolic plane is we plot the nodal degree n, and we plot the vertex degree v. Okay, so if I look at the different things that we've made here, so I could say, all right, well, let me label this. So I go 2, 3, 4, 5, 6, all right? And this one should go, I'll start at 3, 4, 5, 6. So this one right here with vertex degree 6, nodal degree 3, so our hexagons live right there, all right. Where do the rectangles live? So there's a 4, 4 that lives over here. There's also a 2, 4 that lives over here, right? And we have these weird triangles. One of them is a 3, 6 that lives over there. One of them is a 3, 3 that lives right here. All right, why do we care? So what I want to make an argument now is that if I connect these, okay, there's some deep math behind it that I'm not showing you, okay? But if I connect these limits together, what they do is they bound a state space. Now, regular polygons, tessellations made of regular polygons only occupy these points. But it turns out that all convex mosaics live in the area that's bound by those points. What I mean is that the irregular convex mosaics that are made of, random different polygons jammed together, you can show that all of them live within here and none of them live on the other side. So the first point then is if natural fracture mosaics are really convex mosaics, that they're made of convex polygons, all of them should live within here and none of them should live outside of it, right? And second of all, it turns out that these limits that bound the space where convex mosaics can live are really useful for understanding some of the natural cases. All right, so we've drawn these ones made of regular polygons. Let's think of maybe some obvious irregular networks that we can make, right? So you could come up with different ones, but I might say that the simplest random crack network that I can make, if I just wanted to say, well, I know that nature's not regular, I know it's random, cracks just grow willy-nilly. The simplest I can make would be like, I just draw a bunch of random lines or lines at random orientations that crisscross each other, right? And I can look at this thing here, and I can still do the same thing now, right? I can count 1, 2, 3, 4. I can count this other one, and it's 1, 2, 3, right? And if you do this exercise, you will realize that, you know, there's some that have 3s, there's some that have 5s, there's some that have 6s even, right? So they're different if I've drawn the lines randomly. But we can now take the averages, and if you take the averages for this random crisscrossing network, as long as the network is large enough that the statistics are reasonable, right? The average vertex degree formed by this random crisscrossing network is still going to be 4. And the average nodal degree is still going to be 4. So this is an irregular random mosaic, but it's behaving in our symbology or in our representation like it's a grid pattern, right? So this maybe looks more like something you might see in nature, right? That's not the only thing, though. Is maybe a slightly more elaborate model that barely has just a little bit of physical thinking in it is a random model that people call the Gilbert mosaic, which basically is like the random model, except it says, look, I'm going to draw a crack, and I'm going to draw another crack, but every time another crack runs into a previous crack, it stops, right? So if you drew a network like that, sequentially, you imagine you could start connecting these lines, right? And so you just keep cracking the network by drawing random lines that terminate when they hit other lines. Now, why would you do such a thing? Basically, if you zoom in here, the principle is, let's say that I have a crack that already exists, that's spanning the system, and then I have a new crack which is growing, right? It's growing toward another crack. The idea, if you want to inject just a tiny bit of physical thinking, is that once this crack grows into and hits the other crack, you can't transmit an elastic stress across the gap, and therefore that crack should stop, right? So this random model is just a model like where you could do this slicing paper, right? You put a piece of paper down and you slice it with a box cutter or something, and you can just slice through all the other ones. This one here is maybe more like mud cracks. Like the cracks happen in succession, and they're not allowed to jump spaces when they run into other ones, right? So you could draw these two simple random models, the random cut model and the Gilbert mosaic model. And by the way, if you did this Gilbert mosaic model and you measured everything, you would still have that the average number of vertices is 4. But what you would come up with is that the average number of nodes is 2. So that's a random version of the brick wall, right? You can draw these things, and you can ask the question, does nature do any of these? Are there any examples of the sort of most naive model and then the second most naive model, right? And so we're going to look at natural systems. We're going to look at 2D systems, and the system that we're going to start with is mud cracks. So the idea with mud cracks, again, we're not going to go into it too much, but there are a bunch of swelling clays out there in the world, and when we look at materials that form mud cracks, they always have swelling clays in them. What does that mean? It means you have these tiny little clay particles. When they're dry, they're very, very small. But if you add water to them, they suck water into them and they balloon up, right? So if you ever played with the hydrogel stuff or seen it that's in like a kid's diaper or stuff like that, or even other desiccants that people use, right? They're synthetic examples of materials that behave like this, where these small little particles, they suck in water, and they suck in water, and they swell. And so mud, the stuff that we call mud, will basically have a bunch of these clay particles mixed in with sand or something like that, right? So you have sort of an inert species like sand that doesn't really do much when it gets wet, and then you have these clays that when they absorb water, they swell, right? And if you want to think about that, then the consequences for that, let's imagine that we have this mud layer. We're looking from the side, so this is some hard surface that the mud is sitting on, right? And the mud has the sun shining on it. And so, of course, it's evaporating. I should have drawn that in blue. There you go, right? So it's evaporating, so water's coming off, right? So if the clay can swell, then when the clay loses water by evaporation, it shrinks. Now, the clay is sitting there shrinking, trying to pull together, but this mud is also stuck to the substrate that it's on. If I do this in the lab, it's stuck to the table. If this is fresh mud laid down by a river after a flood, the substrate underneath it is just dry mud underneath, right? Some consolidated. So, but this layer of mud is sitting on top of some surface. And so it wants to pull together. And the mud trying to pull together is as if the surface underneath it is pulling apart, right? And so what happens, of course, we're looking from the side, is that you rip open a crack, right? And you rip open a crack in a few places, right? So it cracks here, it cracks here, it cracks here, but I'm just going to draw one because I'm lazy. Now, this is at time 1. At some time 2 later, we come along and we rain on this, right? So we're raining on this. We had this crack, but now the rain comes, sucks in water, the clay sucks in water, the mud starts to expand and stretch out everywhere, and so what happens is that this gets smooshed together, right? And so if you were watching this, it would have the appearance like the crack has disappeared. Now the crack has not disappeared, it's still there, but the clay has swelled together and the two sides of the mud on either side of the cell pushed together like this, right? That happens, and then the sun comes out again, right? When the sun comes out again, a couple things happen. First of all, where that crack was, the crack opens up again. So the same crack gets reactivated and gets opened up. And then also, it can make another new crack somewhere else, right? So there's this shrinking and swelling that's going on. And when it's going on, it's making new cracks, but it's also pushing the old cracks around, right? This is a heterogeneous material. It's not expanding and shrinking at exactly the same rate everywhere. So a crack that formed in one cycle, in the next cycle, it may not be in exactly the same place, right? It's getting pushed around back and forth. And so if you look at this now from above, so at time 0, maybe our initial crack network looks like this, a bunch of T-junctions. And then what happens is that these cracks get pushed around. And the cracks get pushed around, and they go from T-junctions to Y-junctions. And so we call this node twisting. And it might seem kind of mysterious, but it's not actually that mysterious. Basically, what's happening here is that the cracks get pushed around. All of the cracks get pushed around, not just at the junctions, but everywhere. But as the cracks get pushed around by shrinking and swelling and shrinking and swelling, this happens over and over, the cracks will move less when they find a place when they're pushed around less. Makes sense, right? So as the shrinking and swelling is pushing these cracks around, eventually they're going to find a location where they respond the least to shrinking and swelling, okay? That's kind of like their minimum energy configuration. And it turns out that the configuration where these random cracks find themselves moving around the least is going to be a condition when each one of these cracks is maximally distant from the center of every cell. That's where they will move the least. And it turns out that this is a well-known mathematical construct. It's a Voronoi tessellation, right? And a Voronoi tessellation is a statistical equivalent to a hexagonal packing. So remember, if we have regular polygons that are true hexagons, they pack together like a, like a beehive. The irregular random version of hexagonal packing is a Voronoi packing. But statistically, a perfect Voronoi packing is statistically identical to a perfect hexagon packing, right? We would have vertex degree 6, nodal degree 3. So if we look at this on the symbolic plane, what's happening is that initially, I'll draw in a different color. So initially you have the first cracks forming and they're over here. They're like the brick wall. And what's happening over cycles of wetting and drying is that as you're twisting the nodes, you are moving the mud from a brick wall pattern to the honeycomb pattern, right? So they migrate along this axis. Now, the amount that they migrate, of course, depends on the material, how much shrinking and swelling there is. You can imagine how many cycles. If you do this once, it migrates a little bit. Each time you do it, it goes more and more. And so some mud might only shrink and swell a little, and it might be stuck down here. Some mud might have a lot of shrinking and swelling and end up here. But the upshot is that you could basically expect, if this is correct, that all mud cracks occupy some region over here in the symbolic plane, okay? And they do. If you go and you look at where real mud cracks live, some are here, here, but they all occupy a band along here. And we can do, this is a problem that is very amenable to experimentation. Sophie in our lab has been doing these experimentation, and indeed, we can demonstrate that mud cracks migrate along this trajectory, right? And so not only do mud cracks occupy a particular part of the symbolic plane, they're always inside, they're never outside, that they occupy a very particular region, and it's a region where they're either close to brick wall or close to the honeycomb, or they're somewhere in between. And a lot of ones that are in between are probably migrating from one to the other. So let's think about another material. And that material is ice. All right? So I'm drawing it as a sheet just to remind you, terribly, but just to remind you it does have a third dimension, right? But ice floating on a pond, it forms when it gets real cold, but then it has wind stresses blowing on it. It maybe has some, it's being driven if there's convection in the lake from below and all kinds of stuff like that. It experiences thermal stresses because the sun shines on it, so it can expand and contract and all that. And so it cracks. But the one thing that we know about ice is that ice is very well characterized or very commonly observed to have cracks that go through other cracks. So in the mud crack example, that does not happen. When a new crack forms, it runs into an old one and it stops, like the Gilbert model, and like we expect naively from our cartoon. A crack stops when it runs into a previous crack because the elastic stress can't jump the gap. Ice, for some reason, we almost always observe that cracks run through other cracks. And it's not like that they all happen to form at the same time. You can see in ice sheets, we can see this on Earth, we can see this on other planets like Enceladus, that you can tell some cracks are old and barely visible and other cracks are brand new, and yet you have this sequential cracking, but the cracks go through previous cracks. And so somehow cracks that come later are acting like they don't care that previous cracks are there. And it turns out that this is because of a special property of ice, which is that it heals, right? So with the mud over here, we start out with the mud that we have, and it can crack, and then the cracks can get smushed together, but when they get smushed together, it doesn't just blend and melt away the crack that was there. The crack gets preserved. In this situation, basically every crack that gets made gets preserved. In this situation over here, a crack gets formed. Maybe it gets formed because the ice gets ripped apart. Maybe it gets formed from thermal expansion and contraction. But the moment that those cracks form, they start to heal. You know, if you're just thinking about a pond, one reason the cracks can heal is just the sun is shining on it. The surface of the ice melts. You get liquid water, and that liquid water just gets, by gravity and by capillarity, liquid water just gets sucked down into the cracks, and the liquid water makes contact with the ice in the cracks and it freezes again. This is also something that we can do in experiment. If it's a really big ice sheet, which is sinking and pushing down, say, into the ocean, like the Greenland ice sheet, then when a crack opens up, if you imagine that this is an ice sheet that's drafting a lot into the ocean, a crack opens up and just the pressure of the ice pushing down right around it, you rip open a crack and water is going to rush up to reach the same level of the water on either side, right? And so you open up a crack in an ice sheet and the water comes up from below by this pressure until the water reaches a level that's equilibrated with the surrounding. Now you have water inside the crack, and that freezes too, right? In fact, even when you scratch ice, the atmospheric vapor will deposit and freeze on it, and the scratch will heal. So ice is notable for this healing phenomenon. This healing phenomenon turns out to be important because that means that ice has a lot of X's, right? The fact that cracks run through other cracks produces mosaics where there's a lot of crisscrossing and a lot of X's. So if that's true, and that's a special property of ice, we would expect that ice is living somewhere over here at or close to the grid paper pattern, right? And indeed, when we look at cracked ice on ponds, we look at big ice sheets on Earth, we look at icy moons like Europa and Enceladus, what we find is that ice is living over here, closest to the grid pattern, right? And so it tells us that the mechanical processes that are operating and driving the creation and maintenance of these fracture networks leave telltale signatures that you can observe in some simple geometries, right? The mapping of these geometries to our random fracture models, like the random cut model and the Gilbert model, also suggests to us a reason for this commonality or universality, right? That understanding individual crack tip growth can require a bunch of physics, but there's an organization of the network which really comes down predominantly to geometry, and that mechanics enters into the process really just in the context of what geometries are allowed and not allowed. And in this case, it's material properties that dictate that, right? In the case of mud, shrinking and swelling makes the twisting of the nodes. In the case of ice, it's the melting and freezing that gives rise to the healing that ultimately allows this overprinting to happen. Now, everything we've talked about can be extended to 3 dimensions. I'm not going to talk about it, but just to give you an idea, right? So you can imagine pretty easily a 3-dimensional extension right, of the rectangular or square pattern, right? And that's going to be cubes, right? So if rectangles and squares are very common in 2D, cubes are very common in 3D. And indeed, we see them often. Again, when you look at fragments of rock, say at the bottom of a rock outcrop, no individual fragment is a cube. But if you average the hell out of it, you will find that the fragments are cuboids, okay? Similarly, there are three-dimensional extensions of these hexagons, right? And those are the 3D prisms, right? So if you've ever seen basalt columns or anything like that, right, that have their hexagonal in 2D and then they extend down at depth, the formation of hexagonal prisms like basalt columns is actually related to the expansion and contraction that happens in 2D in mud cracks, okay? And so you can learn something from the 2D examples that extend to 3D. So in terms of making these cracks, you know, we talked about this a little bit at the beginning. So we know that, like, just if you imagine a three-dimensional rock outcrop growing a bunch of cracks in it, that you're going to pile up, right, a bunch of cubes here. And so this kind of thing, you know, if you're making cracks on a rock outcrop, it can really be a whole host of things, right? So it can be freeze thaw of water that's in the cracks. It can be thermal expansion and contraction of the rocks themselves, just getting heated up. Remember, real rocks exposed to the surface, there's water around, so water that runs into cracks is going to dissolve rock and weaken it further, right? And so there's a whole host of phenomenon that's going to make these cracks in rocks. But we also talked about a little while ago that once we are transporting particles, like pebbles, right, and they bang into the surface, that they're going to create a bunch of cracks. It turns out, if you zoom in on this process, that if you think of a sharp object, like an initially angular pebble, colliding with the bed, it's regions of high curvature that are sticking out the furthest, that are going to smack into the bed, right? Just like the example I give is like if I throw this eraser at the wall, there's essentially zero probability that the eraser is going to hit the wall exactly on one of these flat faces. It's always going to hit an edge or a corner. And so when you hit an edge or a corner, you generate fragmentation, and eventually you break off that edge or that corner. But in that process, because the pieces that break off are small compared to the pebble, what happens is an initially angular object, the points of high curvature erode the fastest, and the points of low curvature erode the slowest, such that eventually this process of fragmentation, which seems like a roughening process because it makes angular fragments, if the angular fragments that break off are small compared to the parent object, abrasion or fragmentation is actually a smoothing process, right? So you can make rounded pebbles where the pieces that are breaking off by fragmentation are very angular, but they're sand-sized. And so the sand-sized particles are angular fragments, but the large pebble itself is rounding and getting smoother, right? So if we summarize this now, I want to make a point, which is that, you know, we can go around the solar system and we can go around Earth and other planets in the solar system and we can measure here. And we can say, all right, let's look at natural fracture mosaics and where do they live? The first thing I'll tell you is that every fracture mosaic that we've ever measured lives in this domain. So every fracture network that we've ever measured is a convex mosaic. All right? That means then we suspect that these geometric models are actually going to be very helpful for understanding them. The next thing I want to tell you is that the distribution of fracture mosaics in this symbolic plane is not random, and it is not uniform. Nature has preferences. And the preferences, nature prefers either being close to the brick wall, being close to the grid, which is over here, or close to the honeycomb. Sorry, I did it again, right? So there are 3 clusters in nature, and the 3 clusters are actually closest to these 3 points. I told you in the beginning that nature doesn't like triangles. That part of the symbolic plane down there, nature does not occupy. So there are convex mosaics down here, but nature does not make them, right? And so not only do fracture mosaics occupy a restricted part of the symbolic plane, but they actually occupy clusters in the symbolic plane, and there's physical meaning. These ones right here, this is what we call the boring mosaics. Why we call them boring is they're extremely common and they're extremely easy to make. Okay, so if you look at if you look at the glaze that's on your ceramic mug or something like that that you have rattling around in your office, right? It's just like cracks within cracks within cracks within cracks, this hierarchical crack pattern. That is this. Statistically, it's a brick wall. Basically, if you just keep breaking a material without anything else happening, you're going to end up here, right? So successive generative cracks, you just cracks within cracks within cracks. Like so, I form a few big cracks, and then it gets stressed even more, and the cells within that mosaic break again, and then the cells that were broken break again and break again. That has you ending up here. So I call them boring because nothing special needs to happen in order to make these, and these are the most numerous. You find most crack networks in nature are here. These ones here are not boring, they're special. There aren't very many of them, and the only ones we've been able to find are ice. These ones up here, the hexagonal ones, are also more rare. They're also more special. The only place that we find them in nature for 2D is pretty much mud cracks. Things that have experienced expansion and contraction, right? The upshot of all of that is that these special mosaics, at least on Earth and the other planets that we've looked at, their geometry is telling you that water was involved in forming them. We have not found examples of this or of this where water is not involved in their formation. So it says like you could give me a trace of a fracture pattern. Don't even show me the picture. Just give me a trace that you traced off of a fracture pattern, and I could tell you if water was involved in making it, okay? Coming back to the very beginning, we started with plate tectonics. And we said that there was this initially perfect period with this smooth, brittle shell, and then it cracked. And that cracking kicked off plate tectonics, plates colliding together, uplifting and exposing rock, the rock cracking and building piles of rock, cubes, those cubes then getting picked up and banged together as they move down streams, right? Breaking off small sand-sized particles that are also angular, right? The point is that fragmentation is a process that happens across scales, right? I mean, we see thin nanofilms that are fragmented, and we see planetary scale fracture mosaics on planet Earth. So it's this phenomenon that plays out across scales from the planet to grain, and it's fragmentation that made a granular planet, right? So the raw material for all the soil that we observe outside, for all of the sediments that we see in the bottom of the ocean, is rock getting fragmented, right? Broken apart into little bits. Of course, there's other things that happen, animals poop and clays get precipitated. There's other things that get added to this fragmentation phenomenon, but fragmentation provides the raw material basically for all of the soft materials on the planet, okay? That's where we're stopping for today. Questions? Yeah.
Is there something you could say about the scaling of these fragmentations? Like, what is a characteristic length, and does that relate to external factors? Like, is there a characteristic length for the clay? You know, for example, with the swelling and the
Okay. The first thing I'll tell you is, we haven't gotten to universality yet, but fragmentation famously makes power laws, right? So if you slowly stress a rock until it breaks apart, or you shatter it, if you take a ball of plaster and you break it, if you take glass and you hit it with a hammer, right? Whether slow or fast, if you fragment materials, usually you produce a power law distribution of fragments in terms of their size or their area, right? So on the one hand, the thing with power laws, as we talked about a little bit last time, there's no characteristic scale, right? There's no average, at least. So typically in problems in fragmentation, there's not an average scale that's going to tell you much. But remember what I said with power laws, there are cutoffs, right? There is a minimum cutoff and a maximum cutoff, even for things that are power law. They're never power laws forever. And so in the case of drying mud or thin films like that, it's been shown that the maximum size, or you can still take an average of a power law, it's just not very representative, but the maximum fragment size or the average fragment size is related to the thickness of the film. So there's a finite size effect going on there, right? Which is that we're calling these 2D, but there is some intrinsic control of the third dimension on the fragmentation problem, which is it dictates how finely you can break it apart, okay? And basically you get smaller fragments in general when you have thinner films, okay? In terms of the size, there's not really, changing the material properties of this surely changes the size, but not in an obvious way that we understand. Yeah. Similar, though, I would say, is that with ice or anything else, is that in general, bigger systems that are thicker produce larger fragments, and thinner systems produce smaller fragments. But remember that the fragments are power law distributed, so we're just sort of talking about some very crude estimate of size. Yeah. Yeah.
So I don't know if I understand this completely, but if this geometric model for fracture mosaics requires that they have no gaps,
Yeah.
is it the case that this model tends to be more representative of those natural fracture mosaics that involve water because of the healing? I guess I'm kind of stuck on the gaps that happen in mud.
Yeah. No, it's a good question. So I should say that from my perspective, all of the mosaics that we talked about today don't have gaps. Now that seems like a contradiction because they have cracks, right? And in the case of the mud, when it shrinks, the cracks can get pretty big, right? So what I mean is that, first of all, that when we say, the geometric models say that the cracks are essentially infinitesimally small, right? I mean, I draw them as a line. I'm saying, in a picture, they would occupy 1 pixel, right? Now, of course, if I look at real mud cracks and I take a picture of them, I realize that the cracks themselves are not 1 pixel in the picture, right? They occupy some finite width to them. What I would say is that the geometric space that we built is for tessellations that fill space and leave no gaps. And it assumes that the boundaries that we draw as cracks are infinitely thin. The reality is that cracks are of finite width, but they are so small compared to the spaces, to the cells that are between them, that width of the crack is negligible, and it appears not to affect the results. So we're saying that convex polygons that fill space and leave no gaps live within here. And the argument that I made to you, I didn't go around and present measurements to you of the size of cracks compared to the size of the cells, which would be the rigorous thing to do to prove that the cracks are very, very small compared to the cells. But they are. But I sort of did it after the fact justification to say the fact that they all live in here says that that oversimplified model is a good enough description, right? But the way that I'll explain it physically is just that the cracks are very small compared to the cells, such that that approximation, you don't incur very much error. Does that make sense?
It does, yeah, thank you.
Yeah. Well, I think you could say that in all of these systems where the cracks form, you could do a simple geometric transformation and pull them back in, right? So there's gaps, and that's probably why it works. The cracks, it's not just that the cracks are small compared to the size of the cell, but it's rather that even if the cracks are wide, imagine that you just could contract the whole system, is that the cracks would all fill in because these shapes would pull together perfectly. And that's not true with spheres, right? With spheres, you'd pull them together and you'd have some irreducible holes left there no matter what. But with these systems we're making, because the cracks had to form from a solid shell, you can pull the pieces back together and they will fill all that space perfectly.